lecture. So I will be mostly taking this lecture, and just to tell a brief about myself, I've been working in this industry for about 4 years, and we will be just covering the basics of DFT in this course, like what is DFT and all. So that's mostly about this lecture and all. So just to start with, I will just start with what is DFT all about. And in this lecture, what we will be trying to cover is the JTAG architecture. Okay, what is JTAG architecture and how does it work actually? So that's what mostly I will be trying to cover in this lecture. So just to tell about, just to start with, firstly, we need to understand what is DFT all about. Okay, so DFT is basically a emerging branch in electronics right now, and there's many positions open in industry for DFT right now. So DFT is mostly related to design for testability. Okay, we add some design in the chip only for testing purpose. That is what DFT is all about. And DFT consists of some testability features which we need to uh, keep in the design so that after the chip comes out of the fab, we need to check whether the chip is working correctly or not. And that is the use case of DFT. And so in DFT, what we try to cover is the structural faults. That is, if the manufacturing defects are there, or if the fab has done some mistake, then we should be able to point out those mistake. And it is not related to testing the functionality of the chip. So if we are making a CPU, the functionality will be to boot up the CPU and to do different kind of programs. That is all about functionality. But to check that functionality, we have to put that CPU or anything into the motherboard or the socket board. That is not possible for each and every chip that we will be pushing out. Like if NVIDIA is making 1,000 chips, then they cannot put every chip inside a motherboard and check it out, right? That is not even possible because that will take too much of time. So what they try to do is each chip, they will not try to check it functionally, but they will be trying to check it structurally. That okay, there is no manufacturing defects, there is no cross talk between the pins or anything. So that's what we are trying to cover in this DFT, and that's what DFT tries to cover basically. Okay, so anyone has any doubt in this? What is DFT and what is the actual use case of it? Just feel free to ask doubts if you have any, please. Uh, that way it will be interactive. And let's try to be as interactive as possible. Any doubts till now?
No, sir.
Okay. So just then start with. So what we will be mostly covering in this course will be what is DFT, what are the testing mechanisms and fault models, what all fault models are there and what is actually fault model, boundary scan testing, tap controller, and 8PG and BIST and MBIST we will be trying to cover. Apart from this, we can add one or two more topics like that I have in mind, like 1687 architecture and OCC and EDT, that we will just push somewhere in middle or somewhere. But yeah, broadly, you have to cover these topics in DFT. And to get a job into the DFT profile now, mostly I feel you need these topics as well as you need Verilog coding and the Perl coding. Okay, so that you need to get a hang upon. So Verilog coding and Perl coding, we don't plan to cover in the classes. What we have done is we have developed a website where you can go and do your coding exercise. So if you go on this website and you can do the Verilog coding from here. So it has good number of questions and it keeps on adding. So you can just go over here and practice your questions. So if I tell you about this, suppose Mux, if I tell you, and so you will have to create an account over here. And so suppose if I write a code like this. I can run over here. It says answer matched or not matched. If I do a wrong answer, it will say answer matched, and in this one is correct and this one is wrong. So it will say answer not matched. Okay, and you can submit it from here. Basically, that's what this is doing. So while coding, we will not try to cover in the classes because it's very boring. And so because I will be going through if statement analysis statement, that is not needed, I think. So you can go over this platform, you can try the questions yourself, and you can try to pick it up. If you have any doubts, just let me know. I will be able to take 1 or 2 classes depending on the need, if everyone needs it, or I should be able to help you offline somewhere. Okay, is that fine? Okay. Just to go with, where's the page? So that's what we will be doing. We have to cover, apart from these topics, we have to cover 2 more topics, that is Verilog coding and Perl coding. So for Verilog coding, you can use this platform. For Perl coding, our tech team is developing one more section over here related to Perl programming. So we will be able to do that. Okay. So just to start with, let's start with today's lecture. That is all about JTAG architecture. Okay. So firstly, to understand why do we actually need a JTAG? So anyone has any knowledge about it? Like why do we need JTAG and where does it helps? Or do you know what is the 2 pillars on which DFT is based upon? Like if I ask you a more basic question.
It
For
is
running,
IJ tag and J tag.
No. Uh,
Campaign.
no. Any other answers? I'm just talking about not any specific mechanism of testing. I am talking about what are the 2 things that every mechanism needs to provide, basically. And that is basically the basic pillar of DFT, you can consider. 2 basic pillars of DFT.
Controllability and observability.
Yes, that's the one. So anytime you do a DFT testing, no, you have to make sure that you get a controllability of the signal and you get a observability of the signal. By controllability, I mean ki you should be able to control that signal. Whenever you have to write some test, you should be able to drive some value to it. Okay. And observability means basically you should be able to observe certain signals that is needed by your test to say, okay, is it passing or failing? That's what the basic pillars, 2 basic pillar. If I talk about DFT, those are the 2 basic pillars. Scan and all are just mechanism to provide these pillars of DFT. But yeah, these are the 2 basic pillars which you need in your DFT design. Okay, which your DFT design has to provide to you. So just to tell you, so JTAG is just one mechanism through which this is being provided. Okay, JTAG provides. So what you can do is suppose you have to uh, yeah, that one I did it. Hmm. So if I talk about if there's one chip and there's one module, okay, inside this module you need to get a controllability over this pin, and there's one output pin which you need to observe. So one way would be to just pull this out to the chip level, and over here pull this one also out to the chip level, okay, and connect it to a GPIO. One mechanism could be this way, but as you know that today's chip size is like of billions of transistors of or of huge size, no? So there will be many signals which we might need to observe or control. So bringing all of them out to the GPIO is not possible. That is because like that is a extra cost to the company, and only for testing they will not be willing to pull out all the signals to the GPIO, and that is not even possible because there will be again millions of at least millions of GPIOs then in that case. That is not practically possible. So what JTAG actually provides now, it provides a serial interface which can be used for testing. Okay, use which can be used for testing. So in the serial fashion, what happens is we can control using a small number of GPIOs, and there will be not be need for the millions of or billions of GPIOs in the chip. Okay. So, and one more thing that JTAG actually provides us is if in a SOC, suppose we have two or three different IPs from different vendors, okay, and we need to check each of them, then there has to be certain standard which all of these chips has to follow, right? We cannot test each of the chip if they are following different standards for testing. That is not even possible for the SOC vendor. Suppose I am the Dell, I am making a motherboard for my processor, and I am taking different components from different vendors. Then I need a common mechanism through which I can check out all these parts of the SOC or the motherboard. Then if all of the chips are following the same standard, then it will be become easy for me. Otherwise, it will be becoming too difficult for me to test it out. So that's what this JTAG actually provides us. Okay. Uh, is it clear till this point? Anyone has any doubts? So two things I have talked about. JTAG is a serial interface, and JTAG provides us a standard through which we can
Excuse me, sir.
check out multiple. Sorry.
Excuse me, sir. Sir, can you just summarize the what you have said just now?
Yeah, there are two things I have talked about. JTAG provides us a serial interface. Okay. And another thing is JTAG provides us a common standard through which we can check out multiple chips in a SOC. So you understand what is SOC and what is different IPs, or should I go to that level? Is it clear till now? So suppose I am making a Dell and I am taking a graphic card from a different company and a CPU from different company. Then I have to check out in the motherboard both are working correctly or not. So JTAG provides us a mechanism through which we can check out multiple IPs that are present in your motherboard. That's what JTAG is all about. Any doubts in this one?
Sir, can you please elaborate what this serial interface means how practically we are?
Serial interface we will touch upon more. Just give me a minute. Okay. We will touch upon it in the lecture itself. But you got what is the use case of JTAG, right? And how is it providing us?
Yes, sir. Sir, daisy chain will also be explained later.
Huh. Daisy
Okay.
chain will be
Okay.
explained.
Okay.
So, okay. So, just to talk about, as I talked, it's a serial interface. Now we will just touch upon it. So by serial interface, I means if there is a module and we need controllability on 3 pins and we need a observability over 2 pins. So what we will do is we will make a register over here, which will be having 5 pins, five five bits actually, and each one will be controlling this way. Okay, and similarly these all will be connected to this one. So there will be a serial interface. Serial interface, I mean there will be one pin on the chip which will be input, And similarly, there will be one corresponding output through which we can control these signals, like control these 5 registers, 5 bits, or we can observe any of the bit. That's what this is doing. Okay. So is by serial what it means, is it clear? It's basically a shift register on which you are shifting data serially. Like serially means 1 bit by 1 bit. Is it clear now? Whoever asked this question?
Yes, sir.
Okay, cool. The architecture we will understand later, but yeah, this is what the serial means actually. So So what we can do is this output, no, TDI is basically output input and TDO is output you can consider. So in a SoC, if there are multiple chips from different vendors, device 1, device 2, and device 3, you can consider. So we can chain it in a serial fashion as well. Like all the chips can be connected to one TDI, common TDI, okay, which will be in the top level. Basically, at the very top level, there will be only these two pins, TDI and TDO, and through TDI we will be serially shifting in the data because this is one shift register and this is second shift register. So you can connect these two shift registers together and there will be another shift register in device 3. You can connect all of them in a single chain and you can bring it out. That's the beauty of JTAG. Basically, you can check n number of devices in your motherboard at uh, very minimal cost. Basically, there will be only 2 extra pins on your chip, TDI and TDO, and 2 more we will talk about. But yeah, basically 4 or 5 you can check out your complete design. That's the beauty of JTAG architecture. It's very simple and it's very efficient. So in JTAG standard, we have 4 mandatory pins: TDI, TDO, TMS, and T clock. And there is one optional pin that is TRST. Okay. So TDI, as I talked about, it's an input pin. To just serially shift in the data, you need a pin that is known as TDI. TDO is to serially get out the data. So whatever data you are getting out of your chip now, you have to check it out whether it's working correctly or not. Through that, you will get to know that is TDO. TMS is basically to shift between different states and different modes. So TMS, we will be having a better understanding later in the lecture, that when we will just touch upon the tab controller and all. So just hold upon this one. T clock is basically to give clock for the JTAG registers, and TRST is to basically reset the JTAG tab controller and bring it back to the reset state. But one point to remember over here is TRST is an optional pin. It's not a mandatory pin for JTAG standard. Why is it optional? That we will understand again when we will be covering the tab controller. But uh, just remember this thing, it gets asked many times in the interviews and all, that what are the mandatory pins of JTAG and what are the optional pins of JTAG. So you have to answer like whenever someone asks you that, okay, what are the pins needed for JTAG architecture, you have to answer that there are 4 mandatory pins and 1 optional pin that is needed. Okay, so reset is an optional pin. You will be trying to understand why is it optional, because reset should be needed for JTAG, but we will try to understand when we touch upon the tab controller part. So just keep these questions in mind. Why do we need a TMS and why do we need a TRSC? Other than these 3, is it clear till now? Any doubts in these 3? TDI, TDO, and T clock? Okay, let's go ahead. So now we need to understand, we understood, okay, what all pins are there at the top level. Okay, so there are TDI, there's TDO, there's T clock, TMS, and TRST. Okay, we understood that part. But suppose there's a shift register and we need to serially shift in the data into to this shift register or anything. Then what all do we need more? And we need to observe something over here. Okay, and there's one pin and there's another pin over here. And this is a module. Okay. So what do we need more now? What all operations do we need? We need to understand that one. Okay. So first thing is we need a shift operation. Basically, to shift in the data inside this register, you need a shift operation, right? And you need a update operation. So whatever you are shifting, if you are updating on every clock cycle, no. So suppose I need to shift in 10101 into this shift register. So how will my first shift look like? First shift will look like something over here XXXX, and over here first bit will be there 1. Then 1 will be coming over here and 0 will be coming over here. Then 1 will be coming over here, 0 will be coming over here, 1 again will be coming. So if you see this bit, basically it's going 0 1 0 1 kind of toggling, right? And if you keep on updating over here on this bus, then it's an issue, right? Because this will be keep on toggling 0 1 0 1 kind of thing. Whenever you are serially shifting in the data, it keeps on updating over this bus. So if it's a reset or something, no, your design will go for a toss. That your reset is going 0 1 0 1 0 1 kind of thing. That is not even possible, right? And that will also lead to a huge dynamic power dissipation, because every time you shift one bit, your bus will, every bus in the design will keep on toggling. So that's what we need. We need a update operation. Update operation is nothing but whenever your complete shift got completed, no, then only you will update the value from this one to this bus. That's what the update operation is all about. Okay. And another thing is capture operation. Before serially shifting in the data, you need to capture this value onto this bus, because we need to have a observability as well, right? So observability is basically whatever is present on the bus, you need to pull it out into the shift register and serially shift out the data. So that's what the capture operation is all about. Okay. So these are the three operations that we need in a JTAG architecture. Is these three operations clear to everyone? Any doubts in these ones, please ask me.
Sir, the serial data which is coming on the bus, so that bus is basically that similar to I2C.
What do you mean by I2C? Can you please elaborate on that one?
Sir, integrated circuits, like which is a bus for serial communication.
No. That is not bus. I mean just a wire you can consider, okay, which is going to the IP, basically. Okay. I don't mean any protocol or anything over here. It's simple thing you can consider is one JTAG register and one module is there, okay? And this is basically connecting from here to this JTAG register to this module, okay? So this wire you can simply consider. So every time if I keep on updating the value into the shift register onto this wire, no, it will become an issue. That is clear to you?
Yes, sir. Sir, but my doubt is how that serial bits are accumulating on that bus, how it is buffering there.
So what? Okay, that part. So that part we can understand. Just a minute.
Okay, sir.
So that part you will be able to understand over here. Okay. So simple thing is there is one shift register. Okay. And there's one hold register over here corresponding. So this shift register is basically what we talked about till now. Okay. Connected to TDI and connected to TDO. Another thing is this is basically is what is going to your module, which I talked about. No. So these are the 3 pins I need to control. Okay. And these flops are connected to one thing called as update DR. And these are connected to shift operation. Shift and basically your clock. Okay. And this is being connected to over here. So what happens is first you serially shift in the data. Suppose I wanted 0 1 0 1 1. I serially shift in the data. then I will not update while shifting only, no. I will not update this value onto this bus. Once my shift completes, no, I will pulse this update DR pulse, which are connected to these flops, and then only this value will be getting reflected over here. Is it clear now?
Yes, sir. Basically, it is a consist of some flip-flops. That's why it is storing that bus
So
actually.
there it consists of two components. One is shift register and one is update DR flops.
Okay, sir.
And based upon which after the shift completes, you will update it and it will come to this one. And serially, you need to observe this onto this chain, no? So these will be connected to another pin of these flops, and which on getting a capture DR pulse, no, the value which you are getting on these uh, wires will be getting reflected onto this flops basically. It will be transferring through these flops, and you will be able to see it through TDO. So if I tell you about this diagram, so basically there's a TDI pin and there's a shift operation and there's a hold register. Okay, hold register is basically update DR flops, which I've talked about. So serially you will shift in the data, it will get to this shift register. Then the update DR will come, and the value from here shift register will go to this hold register, and it will go out to the data out. Data out is basically over here, the module is connected, okay, through which it will be connecting to some input pin. Similarly, what will happen is the data from here to here, it will be getting connected, and we will be able to observe it out as well. So once the capture DR pulse comes, no, whatever value is there on this bus will be getting accumulated into this shift register. And once shift DR comes, we can just shift out the data out of the TDO. And we should be able to say, okay, if we wanted 1011, are we getting those out of the TDO or not? Is this thing clear? Anyone has any doubts in this one? Please, if anyone has any doubts whenever I am stopping, no, just please ask me over there. I'm not able to control this chat properly. Is it clear? Okay. And one thing, if everything is clear, then answer me this one. Why do we need a JTAG operation? Update operation. Why only capture and shift is not able to be sufficient? Because capture will basically capture the whatever you observability you need, that will give you, and shift will basically give you a operation, basically shift the data into the chain. Why do we actually need a update? Can anyone answer that one?
To update to the register some value.
Why can't we just update it when we are shifting only? Why do we need to update at the end only? Why can't we update it during the shifting? So basically what I have shown 1011, on every pulse we can keep on updating. What is the harm with that?
If we update on every pulse, then the CMOS will charge and discharge the capacitor every time, and it will leads to the dissipation of the power.
Yes, that is one issue. Another issue, basically if your that signal is being connected to some reset, suppose, okay, and that reset has to go to 1 or 0 only, so all the flops will keep on getting reset and deasserted, right? Your design will go for a toss. It might not work correctly after you do the testing, right? So because reset has to go to certain state, basically either it has to go to 1 or it has to go to 0. cannot keep on just toggling 0 and 0 and 0 and can't it? We cannot do that. So that can damage your chip as well. Okay, that is the another issue. Till this part, is it clear to everyone?
So capture is something that we are taking from the output of the chip, right?
Capture is something we are taking out of the chip. Yes.
I mean, from the output states. In the previous diagram, you have connected the input of the chip to the data in. So instead of, I think, I mean, not this one, the chip that we are testing, which will be on the right side.
Chip,
So
yes.
Yeah, so from the outputs of that chip, we connect, we capture the outputs, right?
Yeah, basically we connect it from here to here.
Okay, sir.
Okay.
Yes.
Yeah. Any doubts in this one? Any more doubts?
Sir, we are taking TDO from the shift register. Why can't we? Why do not we take it from the hold register, as done for our like? If we take it from the
Hold
shift
register
register,
is basically what we are shifting over here. That is only going to the hold register, right? Then there's no point in that one, basically, isn't it? Basically, it's just a register that you. So basically, when I showed you this diagram, there was this one pulse, right? And basically, this was being connected to this one, and update pulse was coming. Okay. So basically, your TDI and TDO are connected to this one, these flops, this shift register. This is the shift register I'm showing. If you connect it to this one, there is no TDO connected to it, right? These are going to the IP itself. These are going to the module which you have developed. So
right, sir.
you cannot get the data from these flops. You can get the flops from data from this this one only. Is it clear now?
Yes, sir. Yes, sir.
Okay. Let's move ahead. So till now, what we have covered is basically how the JTAG flop works, what is shift, what is hold, and everything. We have covered basic, what is the basic operation we need for a JTAG to work. Now, how does this capture DR, shift DR, and the update DR pulse comes? That's what we need to understand. So these are basically a control signals, okay, which will be controlling multiple JTAG registers and everything. So how we need to understand how are these control signals getting generated. So these control signals are getting generated through a controller block. Okay, we have a JTAG controller block which generates these signals, basically capture DR, shift DR, and update DR. And based upon this, various operations will be taken care. So what this type controller is basically a controller block only, which takes three signals, that is TMS, TCK, and TRST, based upon which it produces multiple signals. That is capture DR, shift DR, update DR, and capture IR, shift IR, and update IR. Now we need to understand what is this DR and what is this IR. So what is this DR is basically data register, okay? If you need to push in some data into the data, we call it data. If we need to push data into the instruction register, we call it IR. But what is this IR doing? So what is basically this IR? I was just talking about how are these control signals get generated, no? So basically there are two things, data register and IR. So what is this DR and IR? We need to understand, and where the instruction actually comes into picture. So in a chip, there are multiple JTAG registers. There's not only one single JTAG register. Okay. Why do we need multiple? We can consider we can just connect everything in a single chain only, right? Serially, we can connect everything in a serial chain. Why do we need multiple registers, multiple JTAG registers? It's a serial register. Basically, what we can do is, basically, there's one chain, there's another chain. I can just connect it serially. Why do I need to make two separate chains? So suppose this is 100 flops and this is 100 flops. Why do I need to make two chains of 100 flops? Why can't I make a single chain? Any answers?
For redundancy.
What do you mean by redundancy actually?
Let's say if there occurs some fault in one chain, then we can go to other chain for testing purpose.
No, basically this is for testing purpose only. So we will not add more redundancy. It will keep on adding basically. What if this chain fails, this chain fails? Then again we will add another chain. It doesn't work like that way, okay? We add a single flop only for every signal which we have to control. If it is not working, we will take some call. But that is very like that happens in very minimal number of cases. So we just throw out those one or two chips out of the million or the billion chips. It happens sometimes, but we throw out those chips. We cannot keep on adding because it is adding an extra cost to the company as well, right? So we don't add a redundancy over the JTAG as such. Okay. Any other possible answers? That why do we need two separate chains? Why can't we work in a single chain? Basically, all the JTAG flops registers you can just connect it in a single chain. Why do we need a different registers?
Due to clock delay, clock skew.
What do you mean by clock skew? Basically, it's just connecting one output to the other output, right? It's a serial chain. So there's no setup time, hold time kind of concepts over here. Or the skew, clock skew also, I don't think. We can make a tree structure like that way. Basically, clock tree we can make in such a way that, okay, there will be not clock skew or anything. We can make a structure like that way. So the answer is simple. If I need to control this bit, basically it's a 50th bit of this one I need to control. Then how many shifts do I need to do? 100 plus 50? 150 shifts I need to do. Plus basically this one also comes, so total I need to do 300 shifts just to control this bit. Okay. In this one, when I do it basically different registers, how many do I need to do? Only 50 shifts, 100 shifts, and some extra shift to just select this one. So what I can do is a muxing logic, demux logic basically. And this one, and I can just have a select line to just select this one instead of these two. So basically over here, I am able to work with 100 shifts instead of 300 shifts that is needed in this design. Is that correct? Any doubts in this one? So yeah, that's what this diagram is all about. So what we have is an instruction register. We have some muxing, demuxing logic over here, muxing logic over here. Then basically what we are doing is we are selecting a register based on this instruction register. So this is what IR was all about. It's an instruction register basically that is selecting between these multiple registers, which register I need to program. Okay. And a serial, so this data is also coming from TDI only and going out to the TDO. Basically you can read out and program this IR register through this serial interface only. Okay. And this control, basically what we are doing is either we are programming the data register or the control register that comes based upon the tab controller. So what we were covering earlier, we will just touch more into tab controller. But just to explain that IAR and DR concept, I was just covering this one. Is it clear to everyone? What is IAR? What is DR? Any doubts in this one? Is my voice breaking now as well? Or is it audible to everyone properly?
It's clear only, sir.
Okay, cool. Any doubts in what is DR, what is IAR? Okay, cool. Let's move ahead. So this part is clear now. What is DR, what is IAR, what is the use case of IAR, and why do we need a multiple registers? Why can't we work only with a single gene? Now we will be covering this tab controller in detail.
Excuse
Basically,
me, sir.
over here we just, yeah.
Sir, actually, I am not able to understand the concepts clearly.
Which part are you not able to understand?
So from that tab controller onwards.
This one? Hello.
Yes, sir. Onwards tab controller.
So can you ask me a question like which part can you give me more idea? Like you didn't understand. Tab controller I haven't covered completely. Tab controller is basically needs 3 pins only, TMS, TCK, and TRSC, and gives out this control signals. That's what I have said, and I have covered this block diagram. So are you not able to understand why do we need this structure?
Yes, sir. Yes.
So what is your understanding? Can you give a brief about it? What is IR? Why do we need IR? Is it clear to you?
No, sir. Can you repeat the this structure again?
Surely. So we have 3 shift registers, okay? What we can do is we can connect it into a serial fashion. One way was that. Then what is the issue with that one? Suppose I need to control the 50th bit of this one. And each register is of 100 bits. Then how many shifts do I need to do? Whoever was asking the question, can you please answer this one?
Can you repeat the question?
If each shift register is of 100 bits, and I need to control the 50th bit of this register, okay, then how many shifts do I need to do?
150.
150
So
or 300 is
151. 150. Yes.
one, and yeah, or you can consider 300 as well if you need to do the control complete shift, right, from here to here, right?
Sir.
Is
Yes,
it
sir. Yes.
clear?
Yes, sir. Yes.
If you do it in parallel, how many shift do I need to do to control the 50th bit of this one?
50 only.
50 only, right? So that's the benefit. That's why we cannot connect all the registers into JTAG registers into a serial fashion. We need to do it parallelly for multiple registers which are not dependent on each other. So that's why we need a demux logic over here. Okay. Based upon the select lines, one out of these will be getting selected. And similarly, one out of these will be getting to the output. So this logic is that selection process. Basically, out of these 3, which one do I need to select? So that is based upon this instruction register. okay, which will be selecting out of these registers, and similarly selecting out to the TDO. Basically, this one, if you see, this is going to the TDO. So we need two things whenever we need to program a certain register. Suppose bypass register I need to program, or device user data register 1 I need to program. So I need to do two things. Firstly, I will have to load this instruction register, and second thing, I will have to load the data into this register. So one operation is called IR operation, one is called DR operation. IR means loading the instruction, and DR means loading the data. So first thing what we will do is we will load, push the data from this TDI, select this register through the selection marks, and this will be getting selected. Then we will push in the data, whatever we need to program. And similarly, we will observe the data from this one to here. Is it clear now?
Yes, sir.
Okay, good. So just when we were covering the tab controller, we just touched upon what is this GR, what is this IR. Now we will try to understand this FSM in full depth. Okay, so what is this FSM actually? What is this doing? So this FSM consists of 16 states. Okay, if you count these number of states, this will be 16. So what it is doing is this is test reset logic, and this is run test idle. Each state we will understand later. But if you see these two arms, no, it is completely parallel to each other. Basically, it's just operation for DR, same operation for IR, same operation for DR, same operation for IR. Okay, so that's what it is. First state is test reset logic. That is the complete JTAG logic is in reset state. The second one is run test idle. Basically, idle, your JTAG is sitting idle, doing nothing. Okay. Select DR is basically selecting the DR. Basically, which register I need to program and all. This is what happens in this one. Or I need to program the instruction register or the data register, which I was showing over here. That happens in this state. Okay. Then happens the capture DR. Capture DR is basically whatever the data was inside this whole data in, no, you just push it out on this TDO shift register, and that is what it is doing. Okay. Then what we need to do is shift operation. Basically, whatever was there in this TDI, we are just pushing into the shift register, and whatever the data we pulled out of the capture operation, no, we will be able to observe at the same time on the TDO, so that we can compare with a golden output, that okay, 101 is there, so we are able to observe those or not. That's what we are doing. Okay, shifting the data, then exiting the DR, basically exiting the shift operation. Then pause DR. Pause DR is doing nothing, basically pausing for some time. Then exit to DR is basically exiting out of the data register, and at the end we update it. Basically what I've shown, no, update DR, when it comes, the data from the shift register gets to the hold register. So you don't need to understand each and every step of this, like TMS, where is it going, where is it not going. This you cannot remember. Okay, what you need to focus mostly on is this: what is this DR, what is this IR, and these three states: capture, shift, and update. These three states you need to understand, and you need to understand this test reset logic. These 4 or 5 things, if you understand, I think it should be good enough for every electronics interview or anything which asks for the tab controller. No, if you answer these questions, I think that should be enough. One thing that is left in this lecture is this answer, that why is TRST optional? Why is TRST not a mandatory pin? That is because if you see the design of this tab controller, no, it is designed in such a way that if you give TMS equals to 1 for 5 consecutive cycles, no, it will automatically come to test reset logic. You can be in any state. Whenever you give TMS equals to 1 for 5 consecutive cycles, no, it will always come to this test reset logic. That is the beauty of this design. Okay. That's why the industry standard has been made that TRST is optional. If certain company wants to have a TRST, that okay, whenever I pulse the TRST, it should come to test research logic, then they should develop it. If company is saying, okay, I don't want to add an extra GPIO for it, I will just do TMS equals to 1 for 5 times and then it will get reset logic. That is also possible. Okay. And the use case of TMS is to shift between different states. So different states which we were talking about, no, these are the different states which is needed for the JTAG. So any doubts in this one? The complete lecture, basically. This is what I wanted to cover in this lecture. Basically, what we have covered is the JTAG architecture, which is the backbone of DFT. Okay. In the next all lectures, we can just cover fault models, BIST and MBIST and all. Those are the advanced topics of DFT. But this is the basic on which the DFT is being based upon. So if you have any doubts in it, just let me know, please.